Hi guys, so today we're going to be graphing exponential functions as well as log functions. So we're going to look at some of the similarities and differences between the two. So before we work through some examples, I just want to show you guys, remind you guys what the parent functions look like, some of the key points on these graphs, and just a reminder of what some of these transformations do. Now hopefully a lot of this looks very similar to what you guys did in Algebra 2, but I do want to review a couple of these things. So first of all, let's look at the exponential parent function. So the exponential parent function would be something along the lines of y equals b to the x power, where b is your base, and that base can be any number, except for we're not going to see it as 1. And if you think about that, what that could be, if b was 1, 1 to any power is always going to be 1, so that's not actually going to give us an exponential function as a result. That would just be a linear function. So if we look here, if x, we're going to come up with a couple common points no matter what that base is. So for example, if I were to plug in 0 for x, no matter what the base is, anything to the 0 power is always 1. So 0, 1 is on my parent function. Another common point, it would be if I plugged in 1 for x, well then I would always get the value of the base. So 1 comma the base would be an example here. So the one I'm actually going to graph here, I'll graph y equals 2 to the x. So then I would have the point 1, 2. Then what this graph is going to look like, if you think about some of the points on this graph, as those numbers, those x values get bigger, then those are exponentially going to increase. And as my x values get smaller, I would be typing in negative numbers. So 2 to a negative power is going to turn it into a fraction. Like 2 to the negative 1 would be a value of 1/2. 2 to the negative 2 would be 1/4. So these would keep getting smaller and smaller and smaller. What they're never going to do, though, is go below 0. So that means I have a horizontal asymptote at y equals 0. So those are kind of the 3 key points on your exponential parent function. Now, one thing to keep in mind for your exponential parent function, this is your parent function assuming that the base is greater than 1. Okay, if the base is greater than 1. Now, there is the possibility that your base is smaller than 1, but still greater than 0. We're also not going to look at a base of 0, because 0 to any power would also be linear. But if I were to look at a base between 0 and 1, my graph would actually be reflected and would go this way. And again, if you think about the reason why, if I looked at 1/2 to the x power, if I take 1/2 to a negative exponent, it's going to make it a larger number. Like 1/2 to the negative 2 would end up being a larger value. It would give me 4, because that fraction would flip up to a positive number. And that's why my graph would look reflected. Okay, so again, that parent function is assuming your base is greater than 1. So what I want to look at now compared to that is your log parent function. Now the log parent function is actually the inverse of the exponential parent function. So those are inverses of each other. Okay, so your log parent function would be y equals log of some base and then your x as your argument. Okay, so they're inverses. If you remember what that means from Algebra 2, it's when you flip-flop the x and the y. Okay, so what that's going to do is change those key points. So for example, instead of a key point being 0, 1, one of those key points is going to be 1, 0. Instead of 1 comma the base, I'm going to have the base comma 1. And then instead of y equals 0 as an asymptote, I'm going to have x equals 0 as an asymptote. So my log parent function, let's say I graph y equals just regular old log of x. That means 1, 0 would be a point, and then 10, 1 would be a point. Because if there's no base written, that base is 10. So my graph would look like this. Okay, so if you look at those two, they are inverses of each other. If you remember, one of the other components of an inverse is that they're reflections of each other over the line y equals x, which both these graphs are. Okay, so they have very similar key points, but the x's and y's are different. If you can't remember, you can always plug those values in. So for example, if I plug in my x value of 1 here for x, that makes sense because I would have to get 0, because b to the 0 power would give me 1, no matter what b is. If you also remember, we can't have a negative argument for a log. Part of that reason is because of what's happening here on my graph. Okay, there are no values over here because you can't have that negative argument. There's no way to ever get that value based off of that base value that we have. Okay, so what we're going to look at now is transformations. These are going to be very similar to what you guys did in Algebra 2. So if you remember, we have horizontal transformations and vertical transformations. And then which one it affects is dependent on where it's written. If it's written closest to the x, it's a horizontal transformation. If it's written away from the x, it's a vertical transformation. So the first one on here, b to the x plus 1, that is a horizontal transformation because it's next to the x. So that's going to be a shift, and remember the horizontal ones are always backwards. This is actually going to go to the left one. Then b to the x minus 1 would go to the right one. What that actually means in terms of your points is basically you would take the x coordinate and you would subtract 1, or you would take the x coordinate and you would add 1. The next two exponential, those would both be vertical, okay, because that's away from my x. So that would be shifting up 1 and down 1. So I would take my y coordinate and add 1, or take my y coordinate and subtract 1. And then the reflections sometimes get a little bit confused. B to the negative x, it's a horizontal reflection. So it's going to shift it from here to there. So what that means is that it's going to be a reflection across the y-axis. But what that's actually going to do to your coordinates is it's going to make a negative x-coordinate. And then the other one, that's a vertical reflection, so it's going to reflect over the x-axis. But what it's actually going to do in terms of your graph, or the points that you have, you're going to have a negative y-coordinate. Alright, then if you look over here on the right with logs, again, it just looks a little bit different, but the same idea with your transformations. If it's with the x and next to it, it's a horizontal transformation. So that first one would go to the left one, then to the right one, up one, down one, and then again the same type of reflection. This would be a negative x-coordinate. It's going to reflect it side to side, so over the y-axis. And then this one's going to be a negative y-coordinate, so it's going to reflect it over the x-axis. So what we're going to do now is we're just going to look at a couple examples so we can actually transform some of these functions. What we're going to do for all of these is take these key points and transform them using those transformations that we see on there. Okay, so we're going to start with exponential first. So I have this function here. So the first thing I'm going to do is I need to identify what my normal parent function points are. So this is exponential. So my exponential parent function goes through 0, 1, 1 comma the base, and in this case my base is 5, and then has an asymptote at y equals 0. And what we're going to do is just apply whatever transformations we see. So this graph has a shift horizontally to the right 2 and up 4. So what that's going to do to my equation is it's going to take the x-coordinate plus 2, and it's going to take the y-coordinate plus 4. So I'm going to do x plus 2, y plus 4. And then for that asymptote, the change in the x isn't going to make a difference, but shifting it up 4 is going to make a difference. It's going to go to y equals 4. Then I can actually graph this. So I have an asymptote at y equals 4. 2, 5 is a point, and then 3, 9 is a point. So my graph would look something like this. The same shape as that parent function, and that should go closer to the asymptote. It's not a very good graph, but you guys see the general shape there. Alright, same idea on this next one. The only transformation I have here is that I'm reflecting this vertically, so I'm going to have a negative y-coordinate. It's going to reflect it over the x-axis. So there's my key points for my parent function, and then I'm just going to apply those transformations. So I'm going to do a negative y-coordinate, so that becomes 0, negative 1, 1, negative 3, and then y equals 0 is still going to be y equals 0. So what that's going to do to my graph now, you're going to see that it's reflected like we expect it to be, so 0, negative 1, 1, negative 3, and I still have my asymptote here. And there's my graph. Now what's hard about these is it's very difficult sometimes to tell just by the shape of the graph whether or not it's exponential or logarithmic. So if you look at this now, this actually looks like a horizontal shift or a horizontal reflection of your log graph. So the easiest way to tell the difference between your exponential graph and your logarithmic function is to look at the asymptote. Logarithmic graphs are going to have horizontal asymptotes, and exponential functions are going to have, I'm sorry, I just said that backwards. Logarithmic graphs are going to have vertical asymptotes. Logarithmic graphs have vertical asymptotes, and then exponential functions have horizontal asymptotes. All right, so speaking of logarithmic graphs, let's go ahead and look at some examples there. So all we're going to do here is just a reflection. Okay, and we'll see the difference in these two. So remember, these are going to have vertical asymptotes. So the points that these are going to go through, think about your parent function. I'm going to go through 1, 0, the base, which is 2, 1, and x equals 0 as an asymptote. And then the reflection here, this is going to be a vertical reflection, so it's going to be a negative y coordinate. So this should be 1, 0 still, but now 2, negative 1, and still x equals 0. So this graph should look similar to here. And I still have that vertical asymptote. And again, let's pay attention to where our asymptote is so we know the difference between this and my exponential function. So this one has my vertical asymptote, so it's a logarithmic graph. All right, then we'll look at our last one here. This one's going to be a horizontal reflection, so that means I'm going to have a negative x coordinate. So I take my original key points from the parent function, 1, 0, the base, 1, and x equals 0. And then I'm going to transform these. So 1, 0 is going to become negative 1, 0, 3, 1 is going to become negative 3, 1, and x equals 0 is still x equals 0. So then I can draw my graph. And it'll look something like this. And you can see, again, look at these compared to their parent function. If you're not quite sure exactly how to graph them, you can plug in points if you're not sure. You can apply these transformations, but again, look at them compared to their parent function. The log parent function looks like this, and these look like it's been reflected horizontally, which is what we know is supposed to happen. If we look at this one, again, it looks like it was reflected vertically, and that's what we expect to happen here. All right, so the last thing we're going to look at is the domain of log functions. Now this goes for log and natural log. It does not matter the base. And all we need to remember is that the domain is basically making sure that the argument is positive. So what we're going to do is we're going to take this example here. The argument needs to be positive, which means what I do is I take the argument. The plus 3 does not matter here. It's just a vertical shift. It's not going to affect my domain. I take whatever's inside the parentheses, and I set it greater than 0 because I need it to be positive. And then just solve the inequality. So I subtract 6, divide by negative 2, and just remember when you divide on inequalities, if you divide or multiply by a negative, you flip the sign. So I know I need x values that are less than 3, and just be comfortable rewriting these in interval notation, since that's what we see most often. In an interval notation, that would be negative infinity to 3. Alright guys, so that's all we have for graphing. Again, the biggest thing you'll need to make sure you can do is understand transformations to the parent functions, and in particular, you really need to know your exponential and logarithmic parent functions. If you ever are not sure, don't be afraid to plug in some points to see what it should be, but be very comfortable with the exponential parent function and the log parent function, and especially the differences between the two.